Hello everyone, welcome to my YouTube channel School of Chemistry. Today we are going to study about crystal field theory of coordination complexes. That how the coordination complexes are formed, that could be explained by using the crystal field theory. So in this theory, crystal field theory, all the metal ions and ligand they are treated as point charges, and when these point charges approach each other, then the electron cloud of these ligands and the metal they are going to repel each other, and due to that repulsion it causes a splitting in the d orbital of the metal atom or the ion. Now, how the splitting of the d orbital takes place, let us first study about the octahedral complexes. That is, first we will be talking about octahedral complexes. Now, in order to study the splitting of d orbital in octahedral complexes, we must first aware about the shape of the d orbital. So, as we talk about the shape of d orbital, it has five different shapes. Okay, five different shapes. What are these five different shapes? These are the different axes. That is, suppose if this is x-axis, this is y-axis, so we can represent this dxy like this. So this is our dxy. Okay, this is the one shape. Then we have dyz. If this y, this is z, and the lobes are lying in the plane of the y and z axis, we can write it as yz. And one more, we have xz, which is also having the similar shape, lying in the lobes are lying in the plane of the xz plane. So this we call as the dxz. Then we have dx square minus y square. This is your x-axis, this is y-axis. Now in x square minus y square, the lobes of the orbitals are lying along the axis. Okay, so we write it as dx square minus y square, and the last, which we write it as, this is the z-axis and this is the x-axis, we write it as dz square, which has the electron density in the z-axis and the reduced x-axis. So these are the five shapes of the d orbital. Okay, now what happens now if you look at the structure of an octahedral complex. Now this is the metal atom. It to it the six ligands are attached. So if we look at the structure of this octahedral complex, it would appear something like this. Okay, so these are the six ligands, which could be anionic ligands or could be neutral ligands. Okay, four of them will be lying in the plane, and two of them, one above the plane and next above the plane, octahedral geometry. Each of them are perpendicular to each other. Okay, each of them are perpendicular to each other, so we consider them to be as lying along the axis. Okay, fine. So what will happen when these ligands are going to approach the metal ion? Let me directly move to the degenerate d orbital. So this is how we represent the degenerate d orbital. 4 5, this is our degenerate d orbital. Degenerate d orbital means having the d orbital having equal energy. Now what happens in presence of ligand is energy rises up. In presence of ligands, its energy rises up. This takes place in presence of ligands. That is due to the repulsion caused by the electrons of the ligand, and the electrons which are present in this d orbital, due to the repulsion, their energy rises up. When they further approach the metal ion, these five degenerate d orbitals splits up into set of two orbitals. Okay, Now two of them, that is dx square minus y square, whose lobes are lying along the axis, they feel greater force or repulsion, so their energy rises up and they goes upwards, and dz square. And the three of them whose lobes are lying in the plane, okay, they feel slightly less repulsion as compared to dx square minus y square and dz square, so they can be represented in the downward direction. And over here we can represent the energy, that is delta E. This is the energy. Okay, fine. So this is dxy xz dyz. These are, so these set of three orbital we call them as T2G, and the set of two orbital we call them as EG. The center point of these two set of orbitals we call it as barycenter. Okay, and the energy gap between this EG and T2G orbitals we call at delta naught, or crystal field splitting energy. Crystal field splitting energy, out of which, okay, the energy gap between this barycenter and the EG orbital, that could be represented with 0.6 delta naught, and the energy gap between this barycenter and T2G, that could be represented with 0.4 delta naught. Okay, or we can also write as 3 by 5 or 2 by 5. In some books it's mentioned 3 by 5 or 2 by 5, or we can also write it as 0.6 delta naught or 0.4 delta. Okay, this is how the splitting of the d orbital take place in octahedral complex. So this we are talking about crystal field splitting, crystal field splitting in octahedral complexes. Okay, now the turn comes at how to fill the d orbital in the octahedral complexes. Suppose we have a configuration of d1. We don't have any problem. We fill the electron over here. Okay. So electronic configuration comes out to be T2G1. Oh, fine. If we have D2, then the second electron goes into the T2G orbital, that is T2G2. Okay, fine. And if we have 3, then D3, it comes out to be as T2G3. 3 electron goes, and in all the 3 cases, EG will be 0. EG0, EG0. Okay, one more thing I want to mention over here, that this T2G and EG, these are the symbols which are taken from the group theory. Okay, and the alphabet G. G is taken from the word Girard, which means symmetrical. As the octahedral complexes are symmetrical, that's why this alphabet G is mentioned along with T2 and E. Otherwise, these symbols are used T2 and EG only in the group theory. Fine. Now the problem arises when we have 4 electrons in the d orbital, d4. That where to fill the fourth electron? Whether it need to be paired in the T2G orbital or it need to be filled in the EG orbital. Fine. Okay. Now how to decide it, that where to fill the electron? That could be decided with the help of delta naught and capital P, which we call as the pairing energy. Pairing energy. Now what is this pairing energy? Actually the electrons already present in this orbitals, they are going to repel the incoming electron which is coming over there. So it has to, you can say, utilize some amount of energy over there in order to pair it up in the orbital already occupied by an electron. So that we call as the pairing energy. Fine. So in this case we have to take two assumptions, or sorry, two cases. That is case number 1. In that we can take if delta naught is greater than pairing energy. Okay, delta naught is greater than pairing energy. Suppose delta naught is 50 kilojoule and pairing energy is only 10 kilojoule. Then what will happen? in that case, the fourth electron is going to occupy the T2g orbital, and we have the configuration as T2g 4 Eg0. Fine. And in the second case, if delta naught is less than the pairing energy, then what will happen? Instead of pairing up in the T2 or T2g orbital, the fourth electron is going to occupy the higher energy orbital, that is the Eg orbital. So we'll write down the configuration in that case T2g3 Eg1. The same thing happens in case of D5. Okay, when we talk about the 5 electron need to be filled, that in the octahedral complexes, then again you have to take the two cases, that delta naught is greater than pairing energy or less than pairing energy. If delta naught is greater than pairing energy, then we have to write T2g 5 Eg0, and if our delta naught is less than pairing energy, then it would be written as T2g3 Eg2. This will be the configuration over there. So this is how the crystal field splitting is take place, and the d orbital is filled with various electrons in the octahedral complexes. So hope my videos are helping you in your studies. So for more such interesting videos, please like and subscribe to my YouTube channel, School of Chemistry. Thank you.